In the last few lectures, we have seen the calculation of the electric field intensity or the force on a charge present in an electric field based on Coulomb's law. Now we are going to see the calculation of the electric field intensity or the electric flux density using the Gauss law. In this case, only we have to consider the charge density is symmetric. Therefore, we can apply the Gauss law to calculate the electric field intensity or the electric flux density. So, let us start today's lecture on Gauss law. Here, the Gauss law says that the total electric flux psi through any closed surface is equal to the total charge enclosed by that surface, and mathematically we can say the total flux psi will be equals to the q enclosed. Now if we try to imagine that there is a sphere and inside the sphere the charge is present, and due to the charge the electric field lines are coming out through the surface of the sphere. So the total electric field lines which is coming out through the surface of the sphere will be equals to the charge enclosed by that sphere. So if the charge increases, the total electric field lines will increase and the total flux will increase. Similarly, if the q is decreased, then the total flux through coming out of this sphere will be decreased. So here q enclosed is the q charge enclosed by the surface. Now this is the mathematical 5.1 is the mathematical form of the Gauss law. Here the total charge enclosed psi can be written as equals to the surface integral closed surface integral d psi, which is equals to the surface integral of d dot ds equals to q enclosed. Here q enclosed also can be written as the volume integral of rho v dv. Here rho v is the charge density, and from that we can get the equation 5.2, which says that the surface integral closed surface integral d dot ds equals to the volume integral of rho v dv. Now if we apply the divergence theorem to the equation 5.2, then we can get, here you can see that the surface integral of d dot ds equals to the volume integral of rho v del dot d dv. Now comparing these two equations 5.2 and 5.3, we can write that volume integral of del dot d dv equals to volume integral of rho v dv, and from that we can get that del dot d equals to rho v, equation 5.4. So this equation 5.4 is the first of the four Maxwell's equation which we are going to derive, and this one is the first one which we have derived. So now you can see that the equation 5.4, it states that the volume charge density is equal to the divergence of the electric flux density, and also we can see the equation 5.2 and 5.4 are basically stating the Gauss law in different form. Here equation 5.2, which is the integral form of the Gauss law, and equation 5.4, which is the differential or the point form of the Gauss law. And actually the Gauss law is an alternative statement of the Coulomb's law. If we apply properly the divergence theorem to the Coulomb's law, then we can get the Gauss law. And using the Gauss law, we can find out easily the electric field intensity or the electric flux density. Here only we have to consider the charge density or charge distribution is symmetric everywhere, and also we can consider the point charge, the infinite line of charge or infinite surface charge, or the spherical distribution of charge to calculate the electric field intensity or electric flux density. Now let us apply the Gauss law to calculate the electric field intensity or the electric flux density. Now before applying the Gauss law to calculate these two parameters, we need to know some points or some steps we need to follow to use the Gauss law. So here, first point we should consider or we should know that the charge distribution must be symmetric. If the charge distribution is symmetric, then only we can apply the Gauss law. The second point is that if the charge distribution is symmetric or symmetric charge distribution exists, then we will construct a mathematical closed surface which is called the Gaussian surface. This is the step 2. Now after drawing the Gaussian surface, we know that the electric flux density at the surface of the Gaussian surface will be same, and from that we will get the tangential or the normal component of the flux density to the Gaussian surface. When D is normal to the surface, then we will get the D dot ds, which will be equals to D into ds, because we will see afterwards that why, if the component of D is normal, if the D is normal, then why we are getting this one. But if the D is tangential to the surface, then D dot ds will be 0. So we will consider the normal component of the flux density to use the Gaussian surface. So the 4 points here we need to remember. Number 1, to use the Gaussian law, we need to consider that charge distribution is symmetric. When we consider the charge distribution is symmetric, then we can use the our intuition to draw the Gaussian surface. After drawing the Gaussian surface, we need to consider the normal component of the flux density, and from that we will get D dot ds will be equals to D into ds, and the last one, the tangential component will be 0, because D dot ds will be 0, because the tangential component with the normal direction of the area ds will be 90 degrees. So cos 90 is 0. So tangential component, for the tangential component it will be 0. Now let us apply the Gaussian law to calculate the electric flux density for different charge distributions. First, a point charge we are considering, and for the point charge we are going to calculate the electric flux density using the Gauss law. Now, suppose a point charge plus q is placed at the center of the origin of the Cartesian coordinate system. Here you can see that the Cartesian coordinate system we have considered x, y, z, and at the origin of the Cartesian coordinate system we have placed the charge plus q. Now the next step is to draw the Gaussian surface. Now using our intuition, what will be the Gaussian surface? You can see that if it is a point charge, then if we draw a sphere, then we will see that the flux density will be same everywhere on the surface of the sphere. So we can draw the spherical type Gaussian surface so that we can get the flux density same everywhere. So the Gaussian surface which we are drawing, on that the point P we are going to consider, and on that point we are going to calculate the flux density, and the distance or the radius of this spherical surface is smaller. Now since the D is normal everywhere to the Gaussian surface, so the total flux coming out from this sphere will be equals to the charge enclosed. So here we can use the equation Q equals to surface integral of closed surface integral D dot ds, which is equals to the surface integral of dr ar into ds. Here you can see that D is the vector quantity, and that is written as dr, which is the magnitude, and ar. air is the direction of the flux density and which will be normal to the surface of the sphere. So here we will get that dr is the constant value because it is the magnitude taken outside surface integral of ds. Now we know the surface area of the sphere is 4 pi r square. So from that we will get dr into 4 pi r square. So here from that we will get dr equals to q by 4 pi r square. So here dr equals to q by 4 pi r square, where ds, that is the total surface area, also we can find out that the closed surface integral ds equals to surface integral, that is the integration of phi equals to 0 to 2 pi, phi equals integration of theta equals to 0 to pi r square sin theta d phi, which if we calculate we will get 4 pi r square is the surface area of the Gaussian surface, and this idea is taken from the spherical coordinate system. As we got the value of dr, then easily we can find out the flux density d, which will be equals to dr into air. So here the value of dr we got, so d equals to q by 4 pi r square air. So here you can see that if we want to calculate the electric field intensity on that point p, then d we know epsilon naught e, so e will be equals to q by 4 pi epsilon naught r square air. So as we have seen earlier in the case of using Coulomb's law, the calculation of the electric field intensity, that E equals to q by 4 pi epsilon naught r square air, in the same way that the same equation is showing 5.5, that is d equals to q by 4 pi r square air. But here we have calculated easily the electric field intensity at the point P using Gauss law. Only we have considered here the charge distribution is symmetric. Now we are moving to the second topic of application of the Gauss law, that is the infinite line charge. For that case, here also we have considered the Cartesian coordinate system x, y, z, and here in the z axis we have considered the infinite line of charge is placed and the charge density is rho l, which will be in coulomb per meter. Now we want to find out the flux density at the point P. So the same way we can draw the Gaussian surface. The second step is the drawing of the Gaussian surface. So here the cylindrical surface we have drawn, on which the point P is at the surface of the Gaussian surface, and the distance from the z axis to the point P is small r. So using our intuition we need to draw the Gaussian surface. Here you can see that on this cylindrical surface the flux density will be same except the upper area and the lower portion. So here now we are going to use the Gaussian law, that is first we have considered d is the vector and d can be written as d equals to dr air. Now we have to use the Gaussian law or Gauss law, that is phi equals to q enclosed. So q enclosed, for the q enclosed we have considered here, you see that the L length of the Gaussian surface. So the charge density rho L into the length, from that we will get the charge enclosed by the Gaussian surface. So here rho L into L, which will be equals to q, that is equals to the surface integral of d dot ds. Now again the same way, d is the vector quantity which we know that dr into air. So here surface integral of dr air ds. So here we will get from that dr surface integral of ds. Now we know the surface integral of ds we can get from the cylindrical coordinate system, that will be dr into 2 pi r l. So from that we will get the dr equals to q by 2 pi r l, or in the other way we can say dr equals to rho l by 2 pi r. Here one point we should note that surface integral of d dot ds evaluated on the top and the bottom surface of the cylinder is 0. Why? because D has no Z component, that means D is tangential to this top surface and the bottom surface, that is why it is 0. So here D we got rho L into L by 2 pi RL into AR. So LL cancel out, D will get rho L by 2 pi R into AR. So here you can see that using the Coulomb's law we found that the flux density or the field intensity, electric field intensity E equals to rho L by 2 pi epsilon naught RAR. The same equation we got here, just we have considered in this case that the charge distribution is symmetric, and if we consider the charge distribution is symmetric, then the calculation will be more easier. The third topic here, for the infinite sheet of charge we want to calculate the electric field intensity or the electric flux density using the Gauss law. For that case also we have considered that Cartesian coordinate system x, y, z, and we have considered that the infinite sheet of charge is placed at the xy plane or z equals to 0 plane, and the charge density we have considered rho s in coulomb per meter square. Now to determine the flux density D at the point P here, first we need to draw again the Gaussian surface. Here we have considered the rectangular box that cuts the sheet symmetrically and has two of its faces parallel to the sheet. So this one is the Gaussian surface we have considered. Again we need to find out the flux density D. So D is the vector quantity. So here you know that the flux density, the direction of the flux density will be normal to the area, normal to the surface area of xy plane. So here D is equals to dz az because it will be along the z direction, that is why we have taken D equals to dz az. Now we are going to apply the Gaussian law, that is Q equals to surface integral of D dot ds. Here Q we want to find out Q. Q means what? The charge enclosed by this area, the gray area, you can see that the charge enclosed. So here the charge density here is rho s. So surface integral of rho s ds, that is equals to surface integral of D dot ds. So here D, you know that D is decomposed, that D is written in equation 5.9, that dz az, and the direction of the surface, this surface will be in the same way in the z direction. So D dot ds will get dz into ds. So dz into, we have to consider only the upper top surface and the bottom surface. So that is why surface integral of top surface integral of ds plus bottom surface integral of ds. Here you can see that the component of D along the other sides of the rectangular box will be 0 because it is tangential to that point, that is why it is 0. So only the normal component of D we have to consider. So that is why equation 5.2 is valid. That is written here. You see that surface integral of D dot ds evaluated on the side of the box is 0 because D has no component along x axis and y axis. So from that, if we consider the area is A, capital A, so all the area will be A, this area will be A, this area A, this area A. From that we can calculate the flux density. Here you see that equation 5.10 becomes rho s into A, because Q is the Q enclosed means the charge enclosed by the area A. So here rho s into area plus equals to dz into A, the up top surface, plus bottom surface A. So twice of A. So from that we will get dz equals to rho s by 2. So as we got dz, so D from that we can calculate. Here you see that D equals to dz means here rho s by 2 into az. So we can see that if we want to find out the electric field intensity on that point P, then D will be replaced by epsilon naught E. So E will be equals to rho s by 2 epsilon into az, or for general equation an, that you can see that equation 5.11 is similar to the calculation of the electric field intensity at the point for infinite sheet of charge, which we have seen, that is E equals to rho s by 2 epsilon naught an. Now we have to see the calculation of the electric flux density for uniformly charged sphere. So here we have considered a sphere of radius A with the radius A, and the charge distribution is symmetric everywhere or uniform everywhere, and the charge density we have considered, that is rho naught coulomb per meter cube. Now to determine D anywhere inside the sphere, outside the sphere, first we need to draw the Gaussian surface. So here two cases we will consider. First one, that R is the radius of the Gaussian surface, which will be less than equals to A. That means R will be inside the sphere, that is the Gaussian surface will be inside the sphere. And the second case we will consider that R is greater than equals to A, that is that the Gaussian surface is outside the sphere. So first case 1 we will consider. In the case 1 we are going to calculate the flux density. So we have considered the charge has the spherical symmetry. So it is obvious that we need to draw the spherical surface uh, as a Gaussian surface. So for R less than equals to A, the total charge enclosed by the spherical surface of radius R is. That means first we need to draw the charge enclosed by the Gaussian surface. So here you can see that this dotted line shows the Gaussian surface. So we need to calculate the charge enclosed by that surface. So here the Q enclosed will be the volume integral of rho v dv. So that rho v, that is given as rho naught, we have taken volume integral of dv. Now we can calculate the volume integral using the spherical coordinate system. So rho naught is taken outside the integration, surface integral, that is integration of phi equals to 0 to 2 pi, integration of theta equals to 0 to pi, integration of r equals to 0 to r. Here because we need to calculate the charge inside this Gaussian surface, that is why r is taken from 0 to r, not 0 to a. So here r square sin theta dr d theta d phi, from the spherical coordinate system we know that. So after solving that, what we will get, that is rho naught into 4 by 3 pi r cube. So this is the charge enclosed by the Gaussian surface. Now we want to find out the flux coming out, or the total flux coming out through the Gaussian surface. So total flux equals to the closed surface integral of d dot ds, again the same way, equals to dr surface integral of ds. Here surface integral of ds we can find out, that is dr integration phi equals to 0 to 2 pi integration theta equals to 0 to pi r square sin theta d theta d phi. From that we will get dr into 4 pi r square. We have seen earlier how to calculate the surface area of the sphere. So from that we got that the total flux coming out, that is dr into 4 pi r square, which will be equals to the q enclosed, that is rho naught 4 by 3 pi r cube. Now comparing this equation 12 and 13, we have this rho naught 4 by 3 pi r cube equals to dr 4 pi r square. From that dr equals to 1 by 3 r rho naught. So here as we got the dr, we can find out d equals to dr here. So d equals to 1 by 3 r rho naught into air. Now here d we got equation 5.4. Now and this expression is valid when r varies from 0 to a. Now the second case we will consider, that for r greater than equals to 0. Here you can see that r greater than equals to 0 because we have drawn the Gaussian surface outside the sphere. So this radial distance of the Gaussian surface, again we have considered small r. Now the case 2, r greater than equals to a. So here we have the total charge enclosed by the surface is the entire charge placed in the sphere, that is q. Q equals to the volume, q enclosed equals to volume integral of rho v dv. That means rho naught integration of volume integral of dv. So here rho naught and volume integral we know how to calculate, that is integration phi equals to 0 to 2 pi, integration theta equals to 0 to pi, integration r equals to 0 to a. Why 0 to a? You can see that 0 to A because the total charge enclosed by this sphere only, not this sphere Gaussian surface. So we need to consider A radius. So here that is why the charge enclosed we have considered r equals to 0 to A. And so r square sin theta d theta d phi, from that we can get rho naught, and we know the volume of a sphere, that is 4 by 3 pi a cube. In this case, the radius of the sphere A is considered because within this sphere the charge is enclosed. Now we need to calculate the total flux psi, which is equals to the surface integral of d dot ds, the same way that will give us dr into 4 pi r square. So now q enclosed, which is giving, which we will get from 5.15, and which is equals to the total flux. From that we will get d is the flux density, that will be equals to a cube rho naught divided by 3 r square. If you simplify this equation, this equals to this, we will get this d. So that expression of d we will get for r greater than equals to a. Therefore, finally the expression which we will get here, d equals to r by 3 rho naught air for r varies from 0 to a, and the second one, for the second case we will get a cube rho naught by 3 r square air when r is greater than a. Now if we consider the mod of d, we can draw the graph which will give us the idea how the flux density or the field intensity varies with the variation of this small r. That we can see in the diagram. You can see that from the equation, to the first equation, if r equals to 0, then d will be equals to 0. Now r is increasing, you can see that this rho naught and 3 is constant, so d is proportional to r, directly proportional to r, so it will increase proportionally. Here you can see that it is increasing proportionally, and the value will be maximum when r, small r, reaches the value of a. Here if value of a, that maximum value we will get, that is a by 3 rho naught. Here a by 3 rho naught. Now this a is the radius of the sphere. So outside this sphere, if we want to see how the flux density varies, then we need to consider the second case. Here you can see that it is a cube, so and it is r square. So here a is the radius of the sphere, which is constant, rho naught is constant, 3 is constant, so d is varies inversely proportional to 1 by r square. So from that we can find out that it will exponentially decrease, and it will reach towards 0 as r increases. So here that graph we will get due to the value of the second case, that is a cube rho naught by 3 r square. So that is all about the calculation of the electric field intensity, or rather we can say electric flux density, using Gauss law if we consider the charge distribution is symmetric, and the calculations which we have seen here for the point charge, for the line of charge, for the surface charge, infinite sheet of charge, for the volume of charge. Thank you very much, student.